Okay then, so this is me going through Elementary Categories, Elementary Toposes by Colin McLarty. It's a very nice book. It's laconic. It's got a lot of theory there, and I thought it'd be worthwhile to try and make a kind of concise compendium of category theory starting for the basics. No real prerequisites required, but it is quite difficult. But, technically you don't really need to know anything to start. So let's go through it. We start off by defining categories in some simple kinds of arrows. So a category has a collection of objects and arrows between objects. F is an arrow from A to B. That's what this notation means. The domain of F is the source of F is A. The codomain of F is the target of F is B in this case. Each object A has a special arrow called an identity arrow, which we're denoting as 1A. Arrows F and G are composable when the domain of F is the codomain of G. There are three axioms underlying category theory. One is that each pair of composable arrows, F and G, have a composite, which is an arrow called F after G. Sometimes I'll omit the circle, I'll just write this as FG. And that's another arrow that has a domain, which is G, and a codomain, which is F of G, as you can see in this picture here. Okay, and this arrow commutes in the sense that, this diagram commutes this region in the sense that the arrows around this region give the same result. So going along here and then here gives the same result as here. Sometimes I'll denote that with a little green loop like this. Second axiom is about these identity arrows, that in general, for objects A and C and arrows F and G, we have 1C after F is F, and G after 1A is G. Note that this implies that the identity arrow associated with a given object is unique, because if, let's say, 1C and 1 dash C were both identity arrows of object C, then by these properties we'd have that we could either write 1C, 1-C as 1-C or 1C, and they're both the same. So identity arrows are unique for objects. Third axiom is that composition is associative. So basically when we have composable F, G and H, we have that F after G after H is F after G after H, so we can just write that as F after G after H, okay? Right then, they're the basic axioms. Now, an isomorphism is a special kind of arrow from A to B. An isomorphism F, sometimes we'll put a sort of tilde underneath the arrow or next to the arrow to denote that it's an isomorphism. Isomorphisms are characterized by having inverses that go in the opposite direction, so an inverse G, such that FG is 1B and GF is 1A. And we denote the inverse as F to the minus 1. And we'll see later in the exercises that the inverse to an isomorphism is unique. Although there can be many isomorphisms between a pair of objects, but each isomorphism has a unique inverse, okay? When A and B are isomorphic, sometimes we write it like this. A equals B with a tilde on top, sometimes also write it like this. Okay. Another very important kind of arrow is a monic. An arrow F from A to B is called monic, sometimes written with this sort of arrow with a V on the back of it. When it has the property that whenever we have two parallel arrows, X and Y, coming into A from any object T, we have that whenever fx equals fy, that is f after x equals f after y, then we always have that x equals y. So monics basically sort of represent parts of objects. So a monic into B kind of represents a sort of part or sub-object of B. We'll see more about that later. Every isomorphism, every iso. Oh, by the way, monic is short for monomorphism, but we'll usually say monic. Anyway, every isomorphism, that is every iso, we use this abbreviation iso for that. Every iso is monic, since whenever we have fx equals fy, if it's iso, we have this inverse, so then we can just compose with the inverse to get x equals y. An epic, short for epimorphism. An epic is a kind of dual notion to a monic. We denote an epic with double arrows like this. This is an epic from A to B, this F, and it's characterized by the property that whenever we have two parallel arrows, X and Y, coming out of B, we have xf equals yf implies x equals y. Of course, every iso is epic. Again, we can see that by multiplying the right-hand side by the inverses. A category is called balance when every arrow that's monic and epic is iso. The category of sets is an example. In fact, I think any topos is like that. But anyway, let's not get ahead of ourselves. A terminal object, also known as a terminator or a final object, is an object P such that every object T has exactly one arrow from it to P. A couple of important theorems. Oh, by the way, I use this notation upside down capital A to mean for all. And this arrow here, like this kind of big arrow, to denote implies. Okay. I sometimes use a backwards E to denote that there exists, and a backwards E then an exclamation mark means there exists a unique, as in there exists exactly one. Okay, so here's our first theorem then. If P is a terminal object and Q is isomorphic to P, and there's an isomorphism F from Q to P, then Q is a terminal object. Okay, so how can we see this? Well, since we know that P is a terminal object, we know that for any object T, there exists a unique arrow U from T to P, and that means that f to the minus 1 of U is an arrow from T to Q. How do we know it's unique? Well, let's suppose there's another one, so let's suppose V is an arrow from T to Q. well then we have that FV is going to be an arrow from T to P, but there's only one, so we know that FV equals U, and then multiplying on the left by f to the minus 1, we get V is f to the minus 1 U. So that means that this arrow V from T to Q is the only such one, and that means that Q is a terminal object also. Theorem 1.2, any two terminal objects P and Q are isomorphic. And I should add a bit, and there is just one isomorphism P to Q. So that's an isomorphism, we can call it U. Okay, so not only are they isomorphic, but there's only one isomorphism between them. You know, the isomorphism going one way and its inverse going the other way, and there's no other isomorphisms between them. So this is quite clear, because there's only one arrow from P to Q, let's call it U. There's only one arrow from Q to P, let's call it V. It turns out that these are isomorphisms and inverses to each other. So we have to have that VU is 1P, because VU is an arrow from P to P, and there's only one arrow from P to P, that's the identity arrow, so VU is 1P, and conversely UV is 1Q. Okay, so now when a terminal object exists, we know from the above results that, you know, any two terminal objects are isomorphic, and it doesn't really matter which one we pick in some sense. So we just suppose we pick one usually and denote it by 1, and then we denote exclamation mark A to be the unique arrow from A to 1. Okay, this is a dual idea of an initial object, so I is an initial object when there is exactly one arrow from I to any object A, and there are dual results theorems 1.1 and 1.2 for initial objects. We usually let 0 denote an initial object. We sort of suppose we've picked one since they're all isomorphic, and we write again exclamation mark A to denote the unique arrow from the initial object to A. This is much rarer, but a 0 object is an object that's initial and terminal simultaneously, and if there is a 0 object, then all the initial objects or all the terminal objects are all 0 objects because of this kind of isomorphism contagion thing. A generalized element of B is an arrow into B. It's that simple. So an arrow X from A to B is sometimes called a generalized element of B. So this is nothing more than sort of new notation, but it's very useful because it allows us to kind of connect with some of our sort of set theory intuition. So usually we denote a generalized element of B that comes from an object to A as something like X in subscript A, B. Okay, so that denotes that we have this arrow X from A to B. And sometimes that's called, sometimes that X, that arrow is called an A element of B. And sometimes we might call A the stage of definition of X. So we might say, for example, there's a generalized element X of B that stage of definition is A. And that's a fancy way of saying X is an arrow from A to B. Okay? So it's interesting to sort of restate some of the things we've already seen in terms of generalized elements. So, for example, this definition of a terminal object. So P is a terminal object if and only if P has an A element, has one A element for each stage of definition A. Okay, it's a fancy way of saying that P has one arrow into it from every object A. Okay, also our axioms. So this first axiom is just about sort of domains and codomains and composition. And we could say it goes like this. for every arrow F from B to C, and for every A, and for every A element G of F, we have F of G is an arrow from A to C. When I use this upside down A, this for all, and I say G is an A element of F, notice I haven't I haven't mentioned which objects we're talking about, and generally when I do this we're talking about any object, so that there can be any A we can use here, and any B we can use here, and any C we can use here, and so on. Usually it's clear from the context what kind of things I'm allowing to freely vary over. Okay, second axiom then, this is about the identity arrows. So for any arrow F from B to C, we have 1CF equals F. And for any arrow G from A to B, we have G of 1A is G, okay? And then the third axiom, this is associativity. In terms of generalized elements, we'd sort of say for any H from D to A, for any G from A to B, for any F from B to C, we have FG of H is F of G of H, okay? So that's our associativity condition. Now, this is a very, very useful result. This is about when we can tell if two arrows are equal. And it basically allows us to, if we know that two arrows, so say we have an arrow F and an arrow G, and we want to figure out, they're parallel arrows, and we want to figure out, are they the same? So basically what this result says is, one way we can figure out if they're the same is if they, when you compose either one of them after any particular arrow, you always get the same result with the F as you do with the G. So more precisely, an arrow for parallel arrows F and G, we have that F equals G if and only if for any arrow X into A, we have that Fx equals Gx. So how can we prove this result? Well, it's pretty clear that A implies B, because if F is the same as G, of course it acts the same when you do composition with it. Conversely, how do we see B implies A? Well, suppose B and take X to be the identity arrow of A. Well then, we know that since we're assuming B, we know that F of 1 of A equals G of 1 of A, so we have F equals G. Okay, so that's actually a very useful kind of proof technique. Often it is to sort of use, think about what happens with these statements when you put an identity arrow in. Okay, and sometimes an identity arrow of B is called the generic element of B. And sometimes an arrow from the terminal object to B is called a global element or point of, sometimes an arrow from a terminal object to A is called a global element or a point of A. It's denoted by exclamation mark A. Another little bit of terminology. When we have an arrow X from the terminal object to B, we might write when we have x after exclamation mark A, we might write that as a sort of a constant, okay? Because it doesn't really depend on what we do before it, because it sort of goes to this terminal object, the data's lost, and then we sort of reselect this x to work from, okay? So for example, f of k equals x exclamation mark A k, and those two will just compose to be an arrow with a terminal object, so data will get sort of forgotten, etc. So again, it's good to think about the category of sets. You know, very often in category theory, think of this category as this category of sets, which has objects as sets and arrows as functions, and you can gain intuition for what these things mean. Now we can think about more about what these different concepts mean. In terms of generalized elements. So one of the ideas is the idea of a monic. So another way we can say an arrow f from A to B is monic is to say that f is 1-to-1 on generalized elements, because we can see that the definition is basically that for all x and y, which are t elements of A, we have fx, for any t, of course. We have that fx equals fy implies x equals y. That's nice again, because it looks similar to the way we define this sort of thing in set. And also, here's a new definition. So I believe in the category of sets, saying an arrow is a monic is equivalent to saying that it is injective, and saying an arrow is epic is equivalent to saying that it is surjective. But more generally, just saying that an arrow is epic in a category isn't really as strong as all that. A stronger condition would be to say that an arrow f from A to B is onto on generalized elements. And what that means, there's another word for that. It's saying that an arrow is what they call split epic, which is a stronger type of condition than just being epic. But I'll get onto that. But we say that this arrow f from A to B is onto on generalized elements when for any t and for any t element y of B, there exists a t element x of A such that fx equals y. So this again looks very similar to the sort of onto definition we see in ordinary set theory. But there's actually an even simpler, or in some sense simpler, kind of equivalent way to say this, and that's to say, so we have this theorem 1.4. Well, anyway, first just look at this condition B. This is another condition on an arrow. It turns out to be equivalent, and what it says is that there exists, say, arrow G going from B to A, such that FG is the identity arrow of B. So that statement B here, that's equivalent to saying that F is what they call split epic. But we see that this is, well, the theorem is that this is equivalent to saying that F is onto on generalized elements. Okay, so that's so these are all sort of synonymous. So how do we see this theorem? Well, suppose that F is onto on generalized elements, and then consider the case where T is equal to B and Y is equal to the identity. Well, then we have this X such that Fx is ID, or we can call it G, and then we've got statement B holding. So we've shown now that statement A implies statement B. Now let's do the converse. Suppose statement B, and then we want to prove statement A. So we want to prove that F is onto on generalized elements. So let's suppose we've got some arrow Y from T to B. Well then, let's just set, and also of course we're assuming B, so we have this arrow G, which is also called the right inverse of F, or a right inverse of F, I should say. So I'm saying too many things at once. Let's start again. So we're supposing statement B. So we have this G such that FG is identity. And we want to prove statement A. So suppose we have some arrow Y from T to B. Well then, just take X is equal to GY. And then we get Fx is FGY is identity after Y, which is Y. And that means that we must have a statement A hold. So we've shown A implies B and B implies A. And as I say, this statement B here is equivalent to saying F is split epic, and then a G like this is called a right inverse of F, or it's also called a section of F. Okay, there's a dual notion, and it has a dual kind of proof, which I'm not going to go through, but the dual notion is that when our F from A to B has a H from B to A, such that HF equals 1A, then F is called split monic, and H is called the left inverse or retraction of F. Okay. Now, as I say, talking about split epics again, I was claiming that, so when I say dual results, by the way, and duality, I mean when you can get the other concept just by reversing the directions of all the arrows in the category. Okay, I'll get into that more in the next, in a video or two's time. Anyway, one thing I wanted to say is that when F is split epic, then it must be epic. We can see that because assuming F is split epic, we have XF equals YF, implies XFG is YFG, where G is this right inverse, so we get X equals Y. Now, clearly every iso is split epic because its inverse is also a right inverse. So this is our sort of one of our big theorems, and it says that F is iso if and only if F is 1-to-1 and onto on generalized elements. So that's statement B. Statement A is that F is iso. So how can we see this? Well, let's just translate statement B. This is basically exactly saying that F is monic and split epic. Okay, so clearly A implies B because every iso is monic and every iso is split epic. Why does B imply A? Well, suppose B. Well, then F has a right inverse G. So we've got FG is 1B. But we also need the other kind of equation giving an identity arrow. So we get it like this. We write FGF. Now, since we know FG is 1B, we have that FGF is 1BF, which is F1A. And now, since F is monic, we must have that GF here equals 1A here, which is what we wanted. So now we've got FG is 1B and GF is 1A, so we can properly write that G is actually the inverse of F, or G is equal to F to the power of -1. That's what it denotes. And that means that F is an isomorphism.